Welcome to episode 1 of C++ Quant Dev Fundamentals. In this episode, we are trying to set the foundation for everything that follows, and that foundation is the standard template library, vector, and string implementation, because these two containers form the backbone of almost every high performance, low latency C++ system, whether you are building a trading infrastructure or simulation engine or low latency data pipeline, it doesn't matter. This is the main thing. So before diving into this, I want to outline actually what exactly are we going to cover today. And this page in front of me is the roadmap for the entire episode, separating the concept and as well as the practical implementation tasks. So in the theory section here, we have a brief overview of STL containers, and that's like a overview of what STL actually, what containers actually are. And then what are the kind of containers that we have, like vectors, lists, maps, sets, dequeues, unordered containers, ordered containers, and so on, and much more. And understanding the landscape of containers gives you an intuition to choose the right design, right container for the specific problem, especially when performance constraints matter in your use case. So we are not just memorizing containers, we are also understanding their design and their memory model, etc. Then the internal structure of vectors. There we straight zoom into vectors because vectors are the default workhorse in modern C++. We'll discuss how a vector maintains three pointers and how the internal model is crucial to understand why vectors behave the way they do, why pushback is fast most of the time, why reallocations happen, and why iterators become invalid, and how to design around all these behaviors in low latency environment. Also, I'll be explaining what is amortized big O of one pushback, which is one of the most less understood parts by most people who begin C++. And then reallocation. It's not just an internal detail; it's a real consequence, right? It will have cache problems, it will have latency issues, it will directly impact the iterator validity and all. So these topics matter in high frequency systems. And then we talk about the iteration invalidation table, where different operations on the vector like pushback, insert, erase, reserve, resize, each of them have their specific rules when they invalidate the iterators. So we'll try to build a table that shows how exactly which operations can preserve or destroy iterator stability. And this is critical knowledge for C++ low latency. Now, also, we'll talk about a little bit about why low latency and high frequency systems avoid the unexpected reallocations and what are the ways we can do that. Then we'll come to the implementation tasks, and that is first is let's try to implement a mini vector, which is having raw allocation using a new operator, and then pushback that can support both copy and move, and we'll reserve some size, and we'll also give a destructor that destroys elements properly and deallocates the memory. So we'll try to implement our own vector which is already there in the STL, but we'll try to implement it using our own way. And then by understanding these fundamentals ourselves, we can get a deep and mechanical understanding of everything. Now, next is vector reallocation diagnostics. So let's also write code to provide the address of data before and after, and then look at the growth pattern and how reallocation is happening. And let's also benchmark what happens when we use reserve and what happens when we don't use reserve. And by comparing the results, we can actually find out the difference between performance and stability of these vector reserve and vector non-reserve. And then the implementation task is essentially just to implement the table of the theory iterator invalidation that I talked about. So let's begin. Now, what is essentially do we mean by a container, right? A container is not just a vector or list or map. At core, container is like a data structure whose sole purpose is to store collections of data in a well structured, well defined way. And on this page, I just drew a little bit of cloud diagram to understand what essentially goes in an STL container, right? First benefit of STL containers is that they must have a way to iterate using iterators. That is one of the biggest innovations of STL, that traversal is kind of standardized. Instead of every data structure inventing its own way to walk through its elements, STL uses iterators. It's a uniform interface that works on vectors, lists, sets, maps, and everything in between. And this abstraction is what allows algorithms like std sort, std find, and std accumulate to be written once we work on all these containers. And iterators are like the glue that holds the STL design together. Second is that containers must have a well-defined memory model. Every STL container has its own memory layout strategy, right? Vector stores data contiguously. Contiguous in the sense, I'll come to that in a minute. But and then while list can have a node that is scattered across the memory, maps can store it in trees. Unordered maps store it in buckets and hashes. So the way it's internally laid out is different for different STL containers. So it must have a good memory model, and that's crucial for understanding how to write high performance codes. Then is that we need to allow insert and remove elements. So adding elements, removing elements, accessing elements, every STL container must provide a way to do that. And then fourth is we need to see some of the standard time complexities for different operations, right? If you write your own structures, if you write your own data structures using struct, different people may write different functions, and as a result the time complexities would not be standardized. But in the case of STLs, they are basically templates, so they can store all your objects like integers, strings, and user defined structs also sometimes. So as long as the type T that you store inside the vector or the string satisfies the container requirements like copy, move, comparable, hash, etc., the container will hash it without modification. So in 1998 when STL came, this was like a revolutionary thing. Then a generic interface that works for any type T, right? um, I already mentioned this before, that STL can be used to, I mean, a vector can have an integer, it can have a string, it can have anything. So it's like a generic way. You don't have to write different structs for different kinds of input. So also about the time complexities a little bit. Vectors can give you a big O of one pushback, big O of one random access, while lists can give you big O of one insert and erase anywhere. But because list is internally implemented using a DQ data structure, I'll come to that after some time. But it will have a big O of n search. So different containers will give you different time complexity guarantees, and we need to have them standardized, and that's what STL does. So all in all, we must just understand that container is not just a storage, it's a unified abstraction with rules, guarantees, and behavior patterns that the entire STL relies on. Next, why essentially STL, right? Before STL, people wrote their own programs. People wrote their own dynamic arrays, linked lists, trees, hash tables, and this freedom led to disaster. What kind of disaster? So for example, first is memory leaks. Look at this function over here, void bad, int star arr equal to new int 5. So it's basically allocating a dynamic array here of size 5, and when we give size in the zeroth element, when we put it as 10 and arr1 as 20, but we forget to delete arr after that. So it's like memory leak permanently, and these kind of silly mistakes can happen when you write your own methods. Whereas in STL, when you use std vector int arr is equal to 1020, the memory management part is happening automatically. So that's the benefit. Second thing is like segmentation faults. So programmers often frequently access memory that is out of bounds. Usually arrays have a no bounds, out of bounds checking, but nothing prevented writing past that end of allocated array. Right? So a single one-off error can pull down massive systems using crashes. So void bad function over here, it's nothing but it's allocating a dynamic array of size 3. But when we say, so the last element should be in the index 2, but when we try to give arr3 equal to 4, it says out of bounds. And then std vector int a123, if I do a dot pushback 4, it is still safe. It can still add another element. Third thing is like the inconsistent or redundant APIs. In a sense, if you look at this dynamic array A class and dynamic array B class, someone might name the method as add, while someone else might name the method as push. Someone might name the method as int length. Someone might name it as size. Someone might name it as operator int. Someone might just say get to get the index. So it's the same kind of logic, but it's inconsistent across different structs or different classes. And this kind of fragmented ecosystem and like stunted kind of code will make maintenance painful after that. So STL will give you that chance to solve this. Fourth is like the badly implemented structures, right? Where you have this struct node, it has a node data and next, so it's like a forward list, right? And here insert front method uh, is taking a node pointer and allocating a new node to it, and node data is x no, and head is n, but then you forget to assign the next pointer, right? This cannot happen in std forward list int f dot push front 10. It is assigning the next pointer internally. So that is one thing which STL can give you, and that is um, avoiding all these four types of problems. There are many more problems that can happen. But coming back to the point, now that we've agreed on using STL containers, then what kind of STL containers are there, right? Broadly, we can say that STL containers are classified in three types: sequential containers, associative containers, and adapters. Sequential containers are basically containers that store elements linearly in the order that you insert. You can say vector, tq, list, forward list, and array. These are structures that may have contiguous or non-contiguous memory, depends. But someone might be implemented as a contiguous memory, someone might be implemented as a non-contiguous, but uh, like blocks linked to each other with pointers. Internally, like a list, because vector is implemented as a contiguous memory. It has the fastest iteration, and we'll come to that after some time. But dq is a doubly-ended queue. Internally, it's a w-ended queue kind of a structure, so it has a forward pointer and a back pointer, right? And each of those blocks may be stored in some random memory locations, but they have pointers to each other. That makes iteration difficult, that makes latency issues, because contiguous memory will have to just access one location in a memory, and it knows how much length it has to keep navigating to iterate through. Whereas pointers, each time you have to access the new memory location using a pointer. That will cost some latency. So that is sequential containers, and sequential views are nothing but spans and MD spans. A span is a non-owning contiguous view over an array or a vector. They don't own the data, they just view the data. And MD span is multi-dimension span for matrix or tensor like data. In this video, we're not looking at spans and MD spans. We'll only look at vector and strings in the upcoming slides, but just giving you an example of sequential. Now, associative containers. Associative is like you organize the data based on keys rather than their positions. Like associative containers is you associate a key to a particular value, or those keys matter, not the position where they are stored. So if you look at ordered and unordered associative, ordered is like they're implemented as red black trees, guaranteeing we go of log n kind of a complexity. If you've learned data structures and algorithms before, uh, I'll just give you a basic overview of that. Here, if you look at this as the head node, right, and then this is pointing to two child nodes, and so on and so on. if the left subtree height and the right subtree height have not more difference than just one extra row in either of them, not more than that, then it's called a balanced binary search tree. And binary search tree should be like, if this is 10 for example, then all the values over here should be less than 10. So if this is 7, all the values over here should be less than 7 and this should be greater than 7. So this can be like 8, this can be like 5, but 5, 7 and 8 are all less than 10. And the same thing here, if this is 15, this should be like 12 or 13 or 14, this can be 16, this can be, again, because this is the right of 16, it should be more than 16, so 17, and so on. So this is a balanced binary search tree, right? So as and when you start adding more and more elements to the tree, it will iterate through the tree using depth first search or breadth first search, whatever methods, and then it will find the correct position as to where you have to place that number. If I want to insert, say, 11, where would I do that? So it will see it's greater than 10, it will go right, then it's less than 15, go left, it's less than 12, then it will come here and it will add itself as 11, right? So, and if I continuously keep making these the right subtree heavier, then the head node will have to rotate automatically internally. So as of now, the head node is 10 and it's balanced, but if I keep adding more, then if this subtree for example becomes much heavier, then I'll have to rotate and the head node will now become this 15, and then the new node will be like 15, 10, and so on. But we have to somehow keep it balanced. That means the left and the right subtrees should not have a height difference of more than 1. And internally, these set, multi-set, map, multi-map, they are all stored as these kind of red-black balanced binary search trees. So the time complexity should be log n, because each node will have two subnodes and then they'll have two subnodes and so on. So log base 2 of all the elements n will be the height of that tree, max height. So any operation to search a particular element will have to either go left or right each time. So it will not be more than the height of that tree itself. In that case, the time complexity will be big O of log n. Whereas in several sequential containers, the time complexity will be like big O of n, or depends. So that's an ordered associative. In unordered associative, it's giving you big O of one lookup. In the sense it's constant time lookup, because it's using hashing, extra memory, to keep those keys mapped to a particular value by using extra memory. So unordered map, unordered multi-map, unordered set, unordered multi-set. So this difference between multi and normal is just that the multi is allowing you duplicate keys. Like there is one key with a value like apples comma 3 and apples comma 5. If the map is having a string and int, then multi-map can give you apples 3 and apples 5. But if you try to insert apples 3 and apples 5 in a normal map, the apples 5 will update itself into apples 3 and it will remain as apples 5. So multiple key value pairs can remain in unordered, but not in the case of, sorry, not unordered, in multi, not in the case of single. But in unordered it's hashing, and it's ordered it's mostly red black trees. In adapters it's like, um, these are not uh, data these are not new data structures. These are data structures that have already been there in other, like you can use a DQ to make a queue. A DQ is nothing but um, right, a way to go forward and backward. If this is the start node and if this is the end node, I can keep going forward or backward because it has both next and previous pointers. But in the case of queue is like you enter in the line at the last, but you come out in the first. So it's LIFO, last in first out. In the case of stack, you keep entering it inside. So it's first in, and the first element will go at the top, and the same first element will be popped out. So first in, first out. But in the case of DQ, it can be first and last in and first and last out. So this DQ data structure can be used for both stacks as well as queues. So stack and queue internally are based on this DQ or vector kind of a data structure, and they are just adapting on already existing ones. That's why it's called adapters. Um, Priority queues, it's internally using a heap data structure. Priority queue, there'll be a separate video for them, and I'll focus on that in that video. But as of now, these are the bare minimum uh, ways you can classify the types of containers that are there. Uh, Coming to the next, that is choosing the right container. How do you choose the right container to solve your problems, right? In real world C++ systems, especially in quant, in HFT, in low latency context, or choosing the wrong container can simply destroy your performance. So, or even in competitive coding, right? So your default choice should be std vector in this case. Mostly you think in terms of vectors, and there are several extremely good reasons for this. First is that vector has a contiguous memory. We'll come to that. So it's cache friendly. Second is it has lowest latency and fastest iteration. Third is that it has predictable growth, and fourth, it has a light memory usage as compared to any other container. So mostly with default choice, if you can implement that problem using a vector, it's the best. Or hash, if it's big O of 1, then it's even better. But in the case of if you want constant time insertions in vector, you can't insert at the beginning in constant time. Only a pushback is amortized big O of 1, but start is not big O of 1. In that case, you'll have to use DQ. So unless you need uh, insertions at the beginning in constant time, or ordered keys, like you want keys to order themselves in the case of map or set, or hashed lookup in the case of unordered map, then you can not use vector. But otherwise, vector is your default go. Now next is what kind of types are containerizable. So when I say vector int or vector char, vector string, so it's like a vector of strings, right? What is it that I can put inside a vector? Can I put anything inside a vector? No, only what is containerizable, only that I can put in a container. So what do we use to define what is containerizable and what is not containerizable? Right? So when you put an object of type T inside a STL container like vector T, map T, you are giving away the control of that object to the container. So from that point, the container is allowed to move your object in and around in memory if it wants to. It can create copies of your object, it can destroy your object whenever it needs to, it can reallocate memory for that object, it can compare your object with something else in order for sorting or hashing or ordering purpose. If your type does not support these operations, it is not containerizable and you can't put it inside a container. Examples. There are some examples over here of bad types that you can't put inside containers. If you look at here, struct bad, right? What is this? This is a bad bracket. It's like a default constructor. So default constructor bad is invoked when you do bad b. If you create an object b of bad, it will invoke a default constructor. In uh, here bad const bad and delete. This is something not copyable, right? So what is this? This is, we are deleting the copy constructor over here. So if I write bad b bracket over here, bad b equal to a, or bad c bracket a, that is like copying a into b, right? Or copying a into c. This will become invalid if you are deleting it in this struct. So you've deleted the copy constructor, or in this case, bad and equal to delete. This is deleting the move constructor. So now if I have this inside my struct and I then do bad a and bad d is equal to std move a, or move the contents of a into d, it simply gives a compile error. In this case, struct person, it has a name and an age, right? But this cannot be used in a set like set person, because what is it that can make person A greater than B or A smaller than B? How can you say this person is bigger, better, or smaller unless you explicitly define that age is the parameter for that? So for that, even though you've given age in the struct, you need to also write bool operator less than is basically const. If you have two persons A and B, then a dot age should be lesser than B dot age. Only then this that will say person A is less than person B. If you've defined this explicitly, then your constructor becomes then your structure becomes copyable. Otherwise the struct person is not copyable. In the case of point xy, xy coordinates, you can't put that in unordered set because there is no hash function and there is no equal to check. In unordered set, you can have two keys, right? You can have two keys of the same value, you can have two keys of different value but the same key. Now to fix that, you need to add point hash, where these are some arrangements you need to add inside the struct point xy in order to make it either equatable or hashable. Only then you can have it container. But most of these things like int or char, string, these are all containerizable inside the vector or tree or queue or list or anywhere. Now we move into the internals of one of the most important containers of all of modern C++, and that is the vector. Uh, let's look at the implementation of the vector here. Template type name T. This is like the class or templated class with which we start, class vector. And in that there are three pointers mainly. Begin, which is like the start of the allocated memory. End, which is one past the allocated last actual element in the vector, and capacity, which is one past the entire allocated capacity of the vector. If you look at the functions here, the vector begin null ptr, end null ptr, and cap null ptr. This is just an empty vector, no memory allocated yet. So the constructor is initializing everything to null. It's a constructor. The one with the tilde sign here and then vector with the same name as the class, it's the destructor, and here we are just destroying the constructed elements. It has two jobs. One is to destroy all the constructed elements, the second is to deallocate the raw memory. So the deallocation of raw memory is happening somewhere here. Operator delete bracket begin. Now size t, size const, and capacity, these are basically functions to calculate the size of the vector, which is the end minus begin, that is the number of elements currently present in the vector, and const return cap minus begin. Capacity minus begin is basically the entire capacity of the vector. Void pushback, that's a method to add something at the end pointer. So if the end pointer is pointing somewhere here, if you look at in the diagram here, 1584, usually a pointer points to the beginning of the slot here. So the end pointer is pointing to the beginning of the next empty slot, which is where the element is going to be pushed back if I want to push back something in the pushback function. So it's if the end is equal to capacity, or if the end has already come here in this diagram, then you will have to reallocate. Otherwise, a new end will just be the value which has been given as the parameter, and then increase the end by 1. Now in reallocate method, we just take the old size and we calculate the size in that and store that in the old size parameter. Then in the new capacity, we are checking if capacity is equal to 0. If yes, if it then we multiply, then we make it as 1. Otherwise, if it is not 0, then we make it as twice. So it starts with 0, then it becomes 1. So from 1 it becomes 2, 2, 4, 4, 8, and so on. It's as of now it's doubling itself. uh, Allocation of new memory. This is taking a new block and taking the size of the T template itself, the T type itself, and multiplying the capacity by that, and then creating the new block, which is pointing to that new uh, memory in the heap. Now, move or copy elements. It's basically a loop that is uh, moving the old elements to the new block, destroying old elements. It's basically you're going from begin to end, and then using the destructor uh, of that type to destroy that element itself, and then freeing the old memory completely. So the reallocate method is basically allocating the new memory, copying or moving the elements from the old memory to the new memory, destroying the old memory, old elements, and then destroying the old memory, and then updating the parameters like the begin, end, and capacity pointers. So this is basically just the minimal structure of the vector. And note that there is a copy that is applicable to the type. There is a destructor to the type tilde t as well. So clearly the type t is a containerizable type, and that's why we are mentioning it in the vector container itself. And if you look at here in this diagram, 1584 are so far constructed elements. Memory allocated to the vector is this entire big box itself, and the uninitialized memory is where we have yet to store any element. The capacity pointer is pointing at the end of, or one past the end, so it's essentially the start of the new block over at the right side of that capacity, and this is the entire total available memory. So when reallocation is going to happen, what essentially happens is the pointer, or the pointer, if this vector is pointing to this, if this pointer vector is pointing to this object, is going to point to a new object that is twice of that size. Copy or move all the elements from up to down, and then delete the old one. It's a simple way of how you can reallocate. Um, Now CPU usually loads memory in 64 byte cache chunks. Right? If your type is a T, which is 8 bytes, unlike for example int64t, that's a 8 bytes type, then a single cache line will contain only 8 elements. Now uh, iteration is literally running at a hardware speed, so that's the best part. um, Now, no pointer chasing, unlike lists or trees. As I said earlier, in structures like set or map, we are using binary search trees, and there you always have to do a pointer chasing, and elements can be in any random memory as long as the pointer is pointing to the next element. In the case of vector, because the memory is contiguous, uh, there is no pointer chasing. You just need the address to the first begin, and then you can continue iterating through the remaining. Coming to what happens during reallocation, the vector growth. Right? As I said, the entire reallocation process is step by step mentioned over here. So firstly, deciding the new capacity using a growth factor. New capacity is equal to old capacity multiplied by growth factor. Earlier we saw that the growth factor was 2 above. But in the case of libstdc++, which is GCC's C++ compiler, the new capacity is old times 2. In the case of clang, libc++, it is old times 1.5. In the case of MS Visual C++, Microsoft Visual C++, it is new equal to old times 1.5. So vector is basically growing exponentially, not linearly, right? Each time it's 1.5 to the power n number of reallocations that are happening. Um, Step 2 is to allocate the new memory, right? Uh, how is it allocating the new memory? by taking the new pointer and calling the allocator.allocate method to in the parameter is taking the new capacity. Step 3 is to move or copy the old elements using the move constructor. Step 4 is to destroy the old elements. The same diagram I have shown what I have drawn above. And then freeing the old memory using allocator.deallocate. So then the last is to update the pointers, begin, end, and capacity. End will be new block plus old size. Capacity will be new block plus capacity. Now here, if you see, if growth factor is 2, assume for ease of calculation, if growth factor is 2, capacity is changing like 1, 2, 4, 8 till n, whatever the target capacity that you want. So total number of moves, like if the capacity changes from 2 to 4, then you would need to copy the two elements in the old memory to the new memory. That will take 2 moves. If it now changes from 4 to 8, if all 4 have been filled, then while allocating a new memory 8, it has to take all the 4 initial elements and copy them back to the 8, the new memory. So each time it's going to make those old size moves, number of moves. So 1, 2, 4 till n. If where a is the first term in the series, r is the multiplication factor, k is the total number of terms. This can be written as a r k minus 1 dot r minus 1 by r minus 1. A r k minus 1 is nothing but the last term over here. The last term is always written as a times r to the power k minus 1 if there are k terms. So that we know that it is n times 2 minus 1 by 2 minus 1. It's nothing but 2n minus 1. So we know that all these total number moves add up to 2n minus 1. So it is basically big O of n, or n insertions. So if you do it for one insertion, you'll have to divide it by n. So it's essentially amortized big O of 1. So that's the best part about vectors, that it has a amortized big O of 1 capacity. So apart from doing pushbacks all the time, what else triggers growth, right? There are some other methods like insert, which is basically anywhere except at the end, or if memory is full. Like for example, if I'm inserting somewhere in middle, but the memory is full, then you have to reallocate. Or emplace back, that's also having the same rule as pushback. Resize or reserve if n is greater than capacity. In that case also reallocation will be triggered. In move semantics, what we do is um, the middle section of this entire page right here, it talks about uh, what happens when we move elements during reallocation. If you look at this method, for size t I equal to 0, I less than old size I plus plus, new of new block plus I, t std move old block I. Std move is nothing but moving the old elements to the new elements, right? If that type t has a move constructor. Now the dangerous scenario is if you are in a situation where reallocation is happening, halfway through the time a move constructor just throws up an exception, then it's a big mess because half of the elements are in old and other half are in new, while some moves might have been left source object invalid but unspecified states. Like when the move constructor threw an exception, these elements got copied, these remaining elements did not get copied, and one element was getting copied but it is in some source unspecified state. That is where the exception got threw up. So the recovery from this state is tricky, right? So STL, what it does, it takes a safer approach. If at all your type T is clearly specifying a no except kind of a constructor, only then the STL trusts that type and goes ahead with move. Otherwise it first copies all the elements, and once all the elements are copied, only then it deletes the old member. But if you use move semantics, that is, if you don't want any if you can write no except in the move constructor, then move semantics will ensure that there is no copying happening, direct move is happening, and that's going to reduce your latency even more. And that's the best part. So struct my type. If you look at my type, no except that we have written, with no except, reallocation would not waste time copying. It will use move instead and save time. So basically, if you want to achieve lower latencies, you have to use you have to use no except. You have to avoid custom heap allocations. You have to be small and trivially movable, and you have to pre-reserve some capacity in order to avoid the runtime reallocations. And as I said, reserve. Now we come to vector reserve. So one of the most powerful tools for controlling vector reallocation is v.reserve. And what does it do? So you're basically telling the vector, when we say v.reserve n, you're basically telling the vector, if you have please have a capacity for at least n elements. I may not insert them now, but be ready. That's what you're telling the vector. This allows you to avoid unpredictable reallocations later. If your n, or the total number of elements that you're adding or reserving for, is less than the capacity, then the vector does nothing. There is no need of any reallocation. But if n is greater than capacity, then it will allocate a new memory block of at least size n, and then it will move or copy all the elements to the new location, destroy all the old elements and free the old memory, update the begin, end and capacity pointers. But note what stays the same. Size remains unchanged. So this is incredibly important. Reserve is proactive. It's not reactive. Size does not change. Only uh, the fact that it is already reserved before that memory. It's only going to update the begin, end and capacity pointers. So what happens if a type T is 1 GB in size, and if I put it in vector T? If 1 GB is your size that you're going to include as T, and you put it in the vector, then each move is going to be very expensive. Every reallocation is going to duplicate that 1 GB size, which is a huge amount of memory. And every pause, that will freeze the entire system. So cache becomes meaningless in this case, and performance will collapse. So therefore we should never store massive objects directly in a vector. Rather you store pointers to those massive objects. Like in this case vector unique PTR of big object. This keeps vector elements tiny, like just pointers, allowing the fast movement, cheap reallocation and predictable behavior. So this is the golden rule in most systems programming. Now coming to strings. Now when we work with std string, most of us treat it like a simple elegant class that holds text. But underneath that simplicity, the string class is managing memory, capacity and growth using a surprisingly sophisticated internal design. The modern std string object stores three core pieces of information, all inside the object itself. One is, say, size, capacity, and the other is the pointer. So size is where how many characters are actually inside that string. Like hello, it has 5 characters. Capacity, how many characters can fit in that before any reallocation of memory is needed. And pointer to a memory, where characters are stored if they don't fit in the internal buffer. If I give a string uh, hello, how much reallocation does it need to do? Nothing. But if I give a string that's like 300 characters long, is it going to need reallocations? Yes. So how does it manage that internally? That's something that we have to understand. It's actually a duality. Sometimes it's on the stack, sometimes it's on the heap. So that is the key to understanding how strings perform. Sometimes it's the internal string object, sometimes it's the dynamically allocated memory block. So even though the class string looks tiny, it's doing multiple things inside. So there are mainly two modes of string storage. One is the small string optimization, SSO. The other is heap allocation. If it's a small string, what are the rules for that to be optimized. Now, in fact, in large code bases, especially in finance, networking, logging, strings often represent symbols like AAPL for Apple stock, or commands like buy, sell, or tiny labels, or error codes that are shorter than 15 characters. And if we continue to use heap allocations for every one of these tiny strings, it would be disastrous. Right? For modern C++, STL will store short strings inside the string object itself without allocating any extra memory. So the internal buffer typically stores around 15 characters, though the exact number varies by the library. In the case of the SSO, a short string which is around 15 characters on libs std C++ is stored entirely in the string object, where there is an inline small buffer of 16 bytes, where the 15 bytes is those 15 characters. One is for this /0, which symbolizes the end of the string, and the remaining, uh, like in the case of hello, 5 are taken. One is taken for /0, which is symbolizing the end, and the remaining 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 out of 16 are still there, where you can actually concatenate the string and not allocate any new memory. And then there are some other bytes for size and metadata of that string. In the case of heap allocation, A, B, C, D, E, F, G, H, if I have that string till P, length is 16, SSO capacity is 15. So it has to reallocate memory, right? So the 8 bytes out of the entire 24 byte length, 8 byte is stored for pointer to that heap memory. Another 8 byte is for size and another 8 byte is for the capacity. This is usually the case, but in the case of libstdc++, LLVM libc++, which is the Mac OS or Android, and MSVC, which is Microsoft Visual C++, the interpretation is a bit different. In the case of libstdc++, which is GCC compiler, the struct string data has a local buffer of 15, and then there is an unassigned char, one more for size, and the last bit of that, if it is 0 or 1, that signifies whether it's a SSO mode or heap mode. It stores the bit that signifies the mode where the string is kept, and the first 7 bits are basically showing the size. In the case of libc++, there is a char buff of 23 and a size where again is the same, 7 and 1. In the case of a longer string, the char star ptr is used, which points to the heap memory, while size t size and size t capacity. In the case of the capacity bit, the lowest bit of capacity, the least significant bit LSB of the capacity, is storing your whether it's a SSO or whether it's heap, that indication. And in the case of MSPC, the buff of 15 is the uh, it's basically the buffer internal, while the size and mode are all encoded in that same char size element. The last bit again being uh, the the mode itself. So libstd C++, LLVM C++, and MSVC have different interpretations, but eventually it's either 16 or 24. I mean 16 or 23, depending on how big the buffer should be. Next, why do strings actually matter in high frequency trading engines? Now, in high frequency trading, millions of messages can arrive per second. These messages contain extremely short tokens, like order types like B, S for buy and sell, or symbols like ES, NQ, CL, or exchange codes or fixed tags, microsecond timestamps. These are very small strings, and every microsecond matters. Every heap allocation is a potential latency spike. Imagine a trading engine that receives 5 million packets per second and then parses each one of them into short strings. If each of those short strings is going to require a heap memory allocation, the allocator will be overwhelmed, leading to jitter. It will lead to contention inside the malloc, the lock contention, and the stalls that propagate through the entire matching engine. and in extreme cases it will be complete meltdown of the throughput. But in the case of SSO, 99% of these short strings never touch the heap. So eliminating the allocator pressure, avoiding fragmentation and avoiding locks, and maintaining that stable nanosecond precision environment is what we get through these uh, SSOs. So if you want to go into low latency C++ programming, not understanding SSO, not understanding the fact how vector reserve works or how allocations of vector memory works, it's not going to help. It's something that you need to understand. Not understanding is not going to help. Coming to growth strategy of the string, just like the vectors, it's also mostly 2x, sometimes 1x, it's 1.5x. It's usually geometric, right? Like vectors, it reduces the number of mallocs and the number of reallocations required from big O of n to big O of log n over the lifespan of the string. And now it also guarantees the big O of 1 append. Just like in the case of vector, you had a big O of 1 amortized pushback. In the case of string, it's a big O of 1 amortized append at the end. So string str equal to str plus x is not going to cause any latency. It's big O of 1. And also if you use s dot reserve to reduce the copies or allocation spikes, it's going to uh, save you a lot of latency. For example, string message dot reserve 512. In this case, it's reserving 512 size. Uh, and again, even the vector copy versus move semantics works in the case of string as well, where if you are trying to do a new string dot pointer equal to alloc size, and you copy the memory of the new string pointer and the old string pointer, like copy from old to new. In the case of copy, the entire linear copy cost is being used, big O of n. Whereas if you're just moving, like new PTR is equal to old PTR, and old PTR is nothing but SSO buffer, then big O of 1, and that latency will be very low. So returning strings by value, like returning hello world at the end of the function, right? It's it's very cheap. So whenever you want to return a string, right, don't say int main, say string main, or return that string in the function. That will save you latency. Coming to another concept of iterator invalidation. um, Before I go into, now that we've covered the basic theory of strings and vectors, uh, before I solve a couple of practice questions on this, I want to also talk about iterator invalidation. Right? Whenever a vector reallocates, all pointers, references, and iterators, that they become invalid, right? Because the memory itself completely changes. So pushback, if the capacity exceeds, it will cause reallocation. Insert, if it triggers reallocation or resize, reserve, and place, whatever the functions that we saw before, if they trigger reallocation, then they will cause the vector to move its elements from an old memory to a new memory, and because of that, anything that is pointing to the old block is now dangling. And many operations do not affect iterators, like reading the elements. If I just do v of I, read the ith element, or front, back, data, if these elements you're trying to access of the vector, it's not going to cause any iterator problems. But or even pushback without actually exceeding the capacity, just we go of one amortized pushback, that's that's also not going to uh, cause any latency or reallocation. So I just drew a table as to what will cause reallocation and what will not, and whether the iterators will remain valid or not. So reading, modifying, begin, end data, and reserve, all these iterators and references will remain valid, right? But in the case of um, shrink to fit, to shrink the string to fit the size that it is. So capacity becomes equal to size. Or pushback, where capacity is exceeded, like here. Or even some other functions that I have written here, which you can go through and pause the screen. In these cases, most of the vectors become invalid. Most of the iterators, sorry, become invalid. But some of the functions don't invalidate the iterators. And the same table you can draw for the strings as well, where reading a character, modifying a character, pointers, data, and reserve, where there is no reallocation needed if n is less than capacity, or even in the case of pushback where capacity is enough, append basically, or uh, in the case of resize where n is still greater than size and capacity is enough. In that case also the old iterators, old pointers, everything is valid. But some of the other functions which will logically trigger reallocation, there uh, the iterators are not going to remain valid anymore. So let's look at some practice problem for vector as well as string to visualize what we are trying to do here in vectors and strings, and understand low latency string and vector use. Uh, so here I'm trying to implement a mini vector, and I'm including all the libraries, new, cstdlib, cstring, and utility libraries. Uh, we begin with a template class mini vector. In private, we give these three pointers: uh, data, size t, and capacity. Now we define the function reallocate with new capacity being taken in the parameters, and the new block pointer being like a static cast to uh, the operator new that is representing the heap memory, and in that we are just putting the new cap multiplied by the size of that t. So that's the total amount of heap memory that we want. Now we either move or copy the old data, so take a loop till the size and use std move here. After that, we try to destroy the old objects once we have moved them using a loop and a destructor. From I to size, we run a loop, and we use the tilde symbol, tilde t, to use the destructor for those t elements, and then use operator delete. Now we are also updating the data and the capacity. In public, we are giving a mini vector constructor that takes all the null initializations of all the data size and capacity parameters, and then a destructor mini vector in which we are using a loop to destroy the elements of type t, and then also deallocating that memory after the destruction of element is done. Then we are defining a void pushback of mostly we go of one amortized time. It takes the value as a parameter, and if size is equal to capacity, then we uh, constructed capacity by multiplying it by 2. Otherwise, if it is 0 initially, then it becomes 1. So it increases like 0, 1, 2, 4, 8, etc. And each time then we use the reallocate method to allocate that new capacity and then update the size. Now in the case of reserve method, we are using uh, reallocate new cap only if the new cap is bigger than the earlier capacity. Otherwise, we aren't doing anything. And then also use the operator square brackets to return the data of that particular index, and then we return size, capacity, and data, a pointer to the data. So size, capacity, and data functions are also encoded. So that is like a mini vector that I have implemented. Now we go to the mini vector.cpp and we include this mini vector.hpp in that. That's all. We now have a small mini vector kind of a structure. Coming to the next thing, which is the vector reallocation diagnostics. We are taking that mini vector that we made earlier and then uh, putting some basic cout code, and we first initiate the last address pointer as a null pointer, and then for 500 times we are pushing back the element I in the vector v, mini vector v, which we just created. And then we update the array address of the underlying array as void star current equal to static cast of data of the vector. And if current is not equal to the last address, then in that case say that the size is nothing but v dot size and capacity is v dot capacity and data is current, and then make the last address as current. Now after running this code we get all the size, capacity and data, and the data is basically having the address to that value and address of the memory where the value is stored. And now in the analysis, let's see the capacity pattern is at 1248, just like we expected, and then reallocation happens only at sizes 1, 2 and so on till 129 and 287, etc. And then you can see that the address that is changing, only that is being printed at the top. So the first line is size 1, capacity and 1, and then an address. The next line has a different address, and then the next line has a different address, and it's explaining how at every reallocation step the address memory is changing, as you can see. So in the case of 2 it's changing, in the case of 9 for example it's changing. So only when the reallocation is happening, that's when the data pointer is getting changed. Coming to the third implementation, and that is the um, vector growth analysis. If you look at the initials, that is, we're just writing size, capacity, etc. of um, the vector elements, and uh, then pushing back almost 64 different items from 0 to 63, and we're printing the size and the capacity of the vector each time. If you look at the gross analysis of that and run that code, we will see that the size, capacity, and the element, all of them have essentially grown in an exponential manner. If you look at the reserve and no reserve comparison in CPP, let's write some code to actually look at how we can compare reserve and non-reserve. You use the mini vector that we just created. First declare 1 million. Let's try to uh, try to push back 1 million items, right? So we are going to do without reserve, try to push back 1 million items, and then with reserve try to push back 1 million items. We've defined n as 1 million above. So this std chrono duration second is to make a note of the time taken without reserve, and we are printing the size and the capacity uh, without reserve. And we can do the same with reserve. You just have to copy the above code and then change the part where it uh, needs that reserve method, v.reserve. But when we ran it, we got some error because it was not in proper blocks. The local variable problem was coming, and we can solve that by placing both with and without reserve in proper blocks and running the code again. And you can see there's a clear difference that the time taken without reserve is a lot higher than the time taken with reserve. Now let's look at another practice problem here. You're given an array of about 200 million floating point numbers, and you are having to count a moving average of these numbers moving across a window of 64. So moving average is like for the if you look at the example 1 2 3 4 5, if the window is 3, then for 1 and 2 there is no moving average. It needs to have minimum 3 elements. 1 2 3, the moving average is 1 plus 2 plus 3 divided by 3. For 2 3 4, moving average is 2 3 4 uh, divided by 3. And then for the element 5, we count the last 3 elements 3 4 5, add them up, and in that case the moving average becomes 3 plus 4 plus 5 divided by 3. So that is because the window was of size 3. So at every element we can just take that many elements uh, that are there in the window uh, behind behind that element in the array, and then add them up and divide them by the size of the window. That should be giving you the moving average. So we want to calculate that for 200 million different items and want to see the latency with vectors. So first let's define a function to calculate the nanosecond difference between two timestamps. Now we take the window and n values and the array a n and also the array output n. Both of them should be of size n. And now let's fill the data at random. So using float rand percent thousand, we are putting random elements in the A of I for I less than n. Now let's define sum as 0.0f. It's a float value. And then let's calculate for the first window of 64 elements, and let's automate that later. So for the first window, we are just warming up from I equal to 0 to w, sum plus equal to I, and then after that at the end of the loop just say w minus 1, or the last element of output should be sum divided by w. It should not be at the end of the loop, it should be outside. So that will calculate the moving average for the first w elements. And then we now take the timestamps t1 and t2 and calculate the beginning, we calculate t1, and then we run a loop using the sliding window technique from w to n, and there we're just adding the next element and removing the first element in the previous sliding window, updating the sliding window by taking the next w elements and then dividing that output by w each time to and updating that in the output array. And again noting down time after that using clock get time. And then nanosecond should be taking the difference between both the times. And now we try to print the processed n samples window of w, the time it took should be the amount in nanoseconds divided by 1 million for to get the millisecond amount, and then the throughput should be n, that is the total number of elements divided by the time taken in uh, in 1 second, that is divided by 1e9, and then again divided by 1 in exponent 6, 10 to the power 6, to write it as million, that many million operations per second. Let's run this. Apparently 37 nanoseconds or 27 nanoseconds, the amount is too small. It's quite unrealistic. Even the most powerful processors can't do this. So why is that coming for us? It's probably because we have not yet applied the checksum. What's happening is it's probably not calculating throughout all the 200 elements of the output array. So why not just do a checksum to uh, make sure that it is going through the entire uh, output array. After applying the checksum, what it is doing is it's giving us the correct approximate time, or approximately 430 milliseconds, which is an okay time for 200 million records. Coming to strings, we are trying to do the SSO inspection, right? So let's write the code for that. In main for loop, and let's just do it from 0 to 50 and try to print the data capacity and size. So the moment the limit for the loop uh, uh, crosses the fact that we need to now move from SSO to heap memory allocation, that's where you will see the data pointer or the place where the memory is storing the string character, that will change. So the result should show us that clearly at some parts, not all, but at some parts, say from 15 to 16, we see there is a change. Then from 39 to 40, we see there's a change. So clearly there has been a change in the addresses. The next thing we want to see is the copy move comparison, right? The copy constructor and the move constructor comparison. So let's actually push um, about 1 million um, copies, right? And then 1 million moves and see how much time it takes. So trying to write the basic code for that. First would be the copy benchmark. So let's create a copies vector to store that many copies, and let's count the time and start the loop to get the copies and update the copies I as the base. Now count the time again and then check the time difference. Now go ahead with move. In move, create the moves array and then note down the time and then use the std move method. Now again note down the time once move is done and then check the time difference. Now let's compare the times. Let's run our code. There's an error. That's because instead of normal brackets we use square brackets. Yeah. You can see there's a massive difference between copy and move. Move is taking such a small time. And also to track the capacity growth of the string, let's write a small code to print the size, capacity and data, the address, for a limit of 500 length, just like what we did for the vector. So a for loop from 0 to limit, which is in this case 500, and push back the character a 500 times and then check the size, capacity, and address. Let's run our code. And let's see at what points have we seen an address change. 1516, 5960. Yeah. So we can see that even at 680 something we've got an address change. Let's look at another practice problem for strings. Like we have a 200 million character string and we have to see only the tokens from the string. For example, we will have some punctuations apart from continuous words. Apart from those continuous words, we have to print the maximum length of the token word that we got. So it's, for example, if it's like this dot question mark vector something, then the maximum should be vector, so it's 6. So similarly, you can check this code. I upload it on my repository. Let's just once run it. You can see to get a 200 million string, the longest valid token length of 49. It took about that many 100 plus nanoseconds, not more than that. So it's in hundreds of nanoseconds that we can actually get a 200 million length max token size. Okay guys, so that's all for today. Hope you liked the video.